The Innovators Network.
Welcome to the Killer Innovation Show, the longest continuously produced podcast in history. Each week, Phil McKinney brings you the insights and strategies to amplify your creativity and innovation skills. Here's your host, Phil McKinney.
Welcome back once again to the bus. We are here in the mobile studio. We are parked in Richardson, Texas. This is the continuing interviews with a series of innovators, creators, leaders here in Richardson, Texas, telling their local innovation story. What is happening on the ground here in Richardson, Texas? Today's interview is with Voit. Voit is the founder of Additive 3D. It's a 3D printing company. They specialize in unique uses of polymers. The difference being is this is not the traditional 3D printer building, little figurines you stick on the shelf. These are industrial grade parts and items such that you can actually make things that are usable. This isn't about prototyping. It really is about high durability types of materials, both flexible and inflexible. And we get into that whole topic of conversation about what's different about Additive 3D. They recently got acquired by Desktop Metal. For the longtime listeners of the show, you know that we've had a couple of people from Desktop Metal on the show. Desktop has been on the hunt. They've been doing a bunch of acquisitions, consolidating up the 3D printing marketplace. So you want to go back and find those older shows and listen to that, give you a little bit of context. Walt also has a unique perspective. He's an associate professor at UT, University of Texas, in Dallas, around university IP transfer. He actually transferred the intellectual property that became Additive 3D, took it out, created the company, and did it in such a way where there was more than enough benefit for the founders of Additive 3D, the university, the employees, and now with the acquisition of Desktop Metal, everybody came out great. It's a perfect example, real world example of the success of an IP transfer model that fed back in to the owner of the IP, in this case, UT Dallas. So you want to take a look at that. Also, Walt, with being an associate professor, has gotten involved in a lot of university partnerships for research. And he goes in and shares how to approach universities and the kind of coordination and the kinds of things universities can do to actually work in partnership with business around creating and transferring intellectual property. So you want to check that out. Great interview on 3D printing, but also about the origination and transfer of those original ideas into startups, creating a business, and having a successful liquidity event in this form of an acquisition. So before we jump into this week's episode, got one favor to ask: share, like, and follow. Share this episode with somebody who you think would benefit from it. Like it so people see it on your social media, and also just get it out there. Help us get out there. And the best way to do that is follow us on social media. Facebook, LinkedIn. LinkedIn is probably the most active, but I also post on Instagram and other social media platforms. So follow us so that you get kept up to date on the latest information and also where we are traveling to. So again, really do appreciate that. With that, without any further ado, let's jump into this week's episode.
This episode is sponsored by Zoom. With Zoom, you can streamline your communication, collaboration, and creativity all in one place. Zoom is the market-leading platform that provides video meetings, voice, webinars, and chat across desktops, phones, tablets, and conference room systems. To learn more about Zoom and sign up for your free account, visit killerinnovations.com/Zoom.
So, Walt, you are now part of Desktop Metal.
That's correct.
Right. When were you acquired by them?
In May of this year.
May of this year. Because I don't know, I think my listener base is going to start thinking that I'm having a theme of 3D printing. So Adaptive 3D, you do polymer printing.
We do. Well, it's a great thing you have a theme of 3D printing because we see it transforming major segments of the world over the coming decade. We focus on polymers.
So give the listener who's not familiar with polymer printing, what are some of the use cases where people are using Adaptive 3D? What do they do with it? What's the end product or end result that they're trying to produce?
Well, today what we're doing at Adaptive and now via Desktop Metal is producing some of the world's best photoelastomers. And so these are materials that are hard, that are tough, that are tear resistant, but also very strain tolerant. And that's been a real difficult thing to achieve in elastomers, let alone in 3D printable elastomers. And so the innovations that we spun out from UT Dallas allow us to very rapidly print very good materials.
Well, that's always the case, right? Because, I mean, a lot of people, when they think about 3D printing, they think about the early MakerBot type things where you made little chess pieces or, figurines you stuck on a shelf, that type of thing.
Right. And there's this impression that 3D printed parts are weak, that they're brittle, they're prototyping. You want to show a designer what a part could look like, and then they'll go make it out of, quote, real materials. And I think what we've been focusing on, in fact, a lot of the material science community across the country has been focusing on direct additive manufacturing of great materials.
Yeah, and I mean, and the whole issue of, again, additive production, which is really the heart of 3D, right? You start with nothing and then you attach materials and build it up, versus the opposite of that, which is give me a big slab of aluminum and remove material, which is actually pretty wasteful when you think about the traditional manufacturing process. You take a slab of aluminum, you're going to make a part, you're going to lose 75% of that material of being, milled away or processed away type of a strategy. But can you do volume, or is this still kind of in the low volume world?
Well, part of the reason that we joined the Desktop Metal family and the Envision Tech family, and now soon the X1 family, is that we're really on a path toward incredible scale. Right. Rick Fulop, who's running the show, has built an outstanding team that has come from the MIT culture. So Desktop Metal was founded by the chair of the material science department at MIT and some of the lead faculty there that had developed selective laser sintering. You talked to Jonah last year from DM during the COVID crisis, and DM talked about some of the great work they were doing to rapidly produce medical parts and help there. But their vision is shared by us from UT Dallas, but this vision that we can rapidly mass manufacture materials that have good enough properties so the part we're printing can survive aggressive environments. And so today, a lot of printing is limited to tabletop size parts, parts that are the size of a coffee cup or a small hamster. And where we're headed is printing large parts that drive society today, large functional materials.
Well, and it was interesting because when Jonah was on the show, I guess it was 2020, part of the conversation around that also was you innovate the printing, but you also have to innovate the tools to do the printing, because it's a different design process that you have to really think about. Because, I mean, HP, when you're going to build a laptop or a tablet, you design for manufacturability. You're designing ultimately for this factory that's going to produce. And so therefore your entire design is wrapped around that. Well, now you're talking about a completely different way of building a part or a product.
Right.
Do we have the design tools to support this vision or this achievement of scale?
Well, that's one of the really exciting things happening in academia right now and in companies like ours. But it's this new generation of designers that use generative design, that are taking advantage of artificial intelligence, of implicit data representations, and of ways to conceive of goods and make them in new ways, and then building a manufacturing process around that. I think kind of before Desktop Metal and we started, and maybe, to pick on HP a little bit, a lot of the model was printer-centric. It was, hey, let's go build a great printer, and then try to fit materials into that printer. And while that works for a lot of things, if you look at a lot of high throughput manufacturing, a lot of it's, you have tools designed around the nuances of a material. And I think coming out of the material science department at MIT, at DM, and out of the one at UT Dallas for Adaptive, we have this material-centric view of the world. A lot of what we teach our students is these structure property processing relationships. It's not that the same raw material resin or the same set of metal powder is going to yield the same product, but it's what the powder is, how it's processed, how it's post-processed, and then what its resulting geometry is. And all of those working in concert derive how good that material is against the stress-strain tensors that an application would throw at it.
So, okay, I'm even gonna pick on HP, right? Because, one of the precepts that's been baked into the HP printer history is along those lines, but in the case of microfluidics, of controlling the material, right? You want a good print, you want a print that doesn't fade, you want a print that's gonna last for 100 years if you print a photograph of your grandmother and hang it on the wall. And it's a very tight control. But I noticed that in the 3D print world, though, there seems to be a much more open approach to outside suppliers of these raw materials. Is that the case for you guys, or is that a big issue?
So that's a deep and difficult question. The easy answer is that most printers do print lots of different materials because there's not a big enough market for a single material on a single printer yet. Mm-hmm. However, as companies like ours and HP and others in the space continue to serve the needs of large companies at scale, there becomes more and more of a need for tremendous quality control, right, tremendous consistency across tens of millions of parts, hundreds of millions of parts. And there, a lot more sourcing control is required, right, to do that at scale repeatedly.
Right, and that's always been the challenge of whether you do vertical integration or you're doing third-party supplier qualification or whatever is, ultimately if you want to deliver consistency at whatever quality level you choose, the key is consistency.
Right.
Customers have a predicted outcome. They want that outcome to occur 100,000 times.
Exactly. And I think where additive manufacturing is maybe rewriting those rules a little bit is in 3D printing, that consistency is maybe even more important in the end geometry than in just the material by itself. Because as we get to finer and finer resolutions of struts and structures, we get into this regime where surface defects and surface free energy start to dominate over bulk properties. And so when you're printing large coarse parts that are a millimeter or a centimeter in strut thickness, you're still dominated by the bulk properties of a material. But as we get toward 100 microns, 10 microns, 1 micron, all of a sudden, there's this new physics that takes over. There's this thing called surface-free energy that dominates how atoms on a surface behave relative to atoms that are trapped in the bulk of a material. And as we approach that limit, things get really exciting. That's the whole nanotechnology field. But our ability to process and control materials there is really exciting. That's what's driven the semiconductor industry.
Well, that's what I was going to say. You're sounding just like Moore's Law, right? How do I get, transistor geometry down to the size needed for the next generation of doubling the power, reducing the performance, reducing the power requirements?
Absolutely. And it's exactly the mantra that we're following, because as we more intelligently microarchitect materials, we need less mass to solve the same problem. Mm-hmm. So what that means is lower COGS, cost of goods sold. Right. It means greener, lighter, more sustainable. And a lot of times you have green, clean technologies that are more expensive. And so consumers have to make this cost-benefit analysis. Is it worth paying more for something that I think is good for the environment? But in our case, we have this ability to use less material to solve a problem in a more elegant way. And we can pass along that value across the supply chain where everyone wins. And the power of microarchitecture is driving these innovations.
Yeah, I mean, it is interesting, right? Because, well, let me ask you the question. You talked about 1 micron. What is the resolution today? And is there an equivalent to a Moore's law as far as having that size again and having that, at what point does everything fall apart, or is there?
Yeah, that's a great question. Today, that roadmap doesn't really exist in the additive world, although we're starting to see early trends of that. So you've got the ability from photolithography, from semiconductor processing, to already pattern polymers at nanometer size scales. If you look at the incredible work that Texas Instruments, that Intel, that TSMC, that Qualcomm, that others are doing using block copolymers, you can get great edge definition at 14 nanometer nodes, 10 nanometer nodes, 7 nanometer nodes. And so the ability to use light to architect materials is there from the semiconductor industry. The problem has been that photoresists have typically been garbage materials when it comes to thermomechanical properties. They've been a great sacrificial mask to keep you from etching metals in certain steps in photolithography, but you've been unable to support them layer after layer. And so where we're pushing is using semiconductor technology. And in fact, we take advantage of Texas Instruments DLP technology to drive this innovative roadmap. So Texas Instruments can build these DLP chips with mirrors that are 5 or 10 microns on a side. So we're already at the size scale. And by routing light across these mirrors, we can simultaneously pattern millions to billions of bits of information. And we can do that tens of thousands of times a second. So right now, there are a lot of competing 3D printing technologies in the polymer world that all can sort of do low volume and mid volume manufacturing. But we see top-down DLP head and shoulders dominating the other technologies over the coming half decade because of the cost of patterning a bit of information. We can power a single mirror with picoamps or femtoamps of current, and TI can build these mirrors for 1,000th of a cent per mirror. So our cost per bit of information is orders of magnitude cheaper than lasers, than inkjet nozzles, than injection molding. And so as our technologies scale, we have the ability to build incredible microarchitecture at very large size scales, but do that very inexpensively.
Yeah, well, I think that's the interesting combination. Going back to your topic about green, right? Because there's always been this trade-off between, well, I can go green, but it's going to cost me 30% more, 40% more. Is there a way to get green and get to a lower cost per unit volume, as an example?
Absolutely. And if you can use less material, so in some of the injection molding and blow molding and VARDM, vacuum-assisted resin transfer molding, or extrusion industries, the tools have been commoditized, and the driving cost per part is the material cost. And so if by the power of microarchitecture, we can reduce the material consumption by 30%, by 50%, by 90%, it turns the cost structure of producing goods and services on its head. Right. And that gives us incredible ability to pass on that value across the supply chain to customers, and everyone along that process wins.
I guess, though, there's a lot of still discovery that has to happen, right? Because you were talking about materials, right? And you think you know how material is going to act. You start trying to take out 30, 40, 50, 60% of material. Typically in the past, when you've done that kind of manufacturing, the engineers throw a little bit extra in there because it's not quite sure they want this thing to survive a crash, or they want consumer dropping it on the floor, not breaking. So my guess is, again, going back to the tools required to get to that kind of reduction on raw materials is not an easy tool to build.
It is not. And then the software that's driving things at this resolution is also very, very difficult.
Right, because I think, it was Desktop Metal talking. We had a couple of different conversations with them with regards to this AI model that then you kind of put in the stress points, what it had to be able to do, and then it went through and iteratively digitally designed it and tested it to see if would it survive, and then get out as much of the material as possible.
Exactly. There's a software program called LivePart and LiveCenter, and we do this iterative topology optimization to predict after sintering, in this case we're talking about metals, after you've printed a part, depowdered it, and then put it in a furnace, how it will shrink so that you can design the part a priori so that it shrinks into the right geometry at the end.
Right.
And that became a very powerful tool that's enabled Desktop Metal to print an order of magnitude faster than a lot of our competitors and still result in parts with incredible thermomechanical properties on the metal side.
Right. So talk to me a little bit about the relationship Adaptive 3D has with UT Dallas.
So Adaptive 3D is based here in the heart of DFW. We're a few miles from UTD. We're a few miles from Texas Instruments headquarters. And although we technically spun out when I was a graduate student back at Georgia Tech, the core technology that we built was done at UT Dallas. I'm an academic from UT Dallas. I'm an associate professor of material science and engineering and mechanical engineering. And this was some work that originally spun out of DARPA-funded work. I was very fortunate at the university to be a DARPA Young Faculty Awardee. We had this fire hose of funding from the Defense Department to innovate on these so-called thiol chemistries. A thiol is the sulfur analog of an alcohol. It's an SH group. And we were building substrates for photolithography, for clean room processing. We were essentially building computer chips on thin film plastics. And what's really neat about these thiols is there's a fundamentally different reaction chemistry that takes place in thiols called chain transfer instead of chain growth, which happens in a lot of free radical polymer systems. So what that means is instead of a single polymer chain growing lots of monomers and getting to be millions of Daltons maybe long, we'll grow these very short chains and then transfer the radical to another growing chain. So we're building these really short segments, and at the very last step of the process, everything clicks together. So what this does is it reduces cure stress. This sounds like a really in-the-weeds, esoteric materials description. It is, but the key importance is that because we don't have cure stress, we can heat up these materials, we can freeze these materials, and we don't evolve stresses in the material. That means if we want to stick thin film metals to these materials, we can thermally cycle them and they survive. That means if our 3D printed parts want to work in sub-zero temperatures, in fact, down to negative 60 degrees C, we're still great elastomers. If they want to work up at 100 degrees C, we're still great elastomers. If you look at a lot of the world's rubbers today, they get really brittle at low temperatures and are not good solutions. Or at high temperatures, they get soft. A lot of them melt, they fall apart. You maybe put a G.I. Joe, on a hot skillet as a kid, and seen it melt away. A lot of thermoplastic processing is the melt processing of materials. Well, we have this incredible thermal control of materials over huge ranges that allows us to dictate great properties in the ranges that you need for automotive, for aerospace, for consumer, for industrial applications that haven't been met before in the industry.
So you're an associate professor at UT Dallas. I get corrected by Paul Volcker. UT Dallas at Richardson. He always wants to make sure to get the Richardson name in there.
There you go.
I've been involved at University of Illinois and Urbana-Champaign with Dr. Phil Phillips, who does tech transfers and all that. In this case, it was work done both at UT Dallas with DARPA funding. Did you have any hesitation? What was the roadblocks you got from taking that work and turning it into Adaptive 3D?
Well, luckily, UT Dallas has been a pioneer in tech transfer, even though UTD is a very young university. In fact, in 2019, I think we were rated the #1 university in the U.S. under 50 years old. It was founded by the founders of Texas Instruments. And with civic leaders like Mayor Volcker, who spent time at HP, there's this incredible drive in Dallas to solve practical problems for industry. And that's been in the roots and in the DNA of UT Dallas. And so as the tech transfer program emerged, earlier under the leadership of Bob Robb, and now under Joe Pancrazio and Brent Schultz, there's been this real drive to enable founders, to enable inventors, to enable tech transfer, to have the university play a supporting role where it can, and get out of the way bureaucratically where it can, to let innovation flourish. And part of that is because we maintain such close ties, between or among industry and UT Dallas, these mechanisms have been very well honed. Mm-hmm. And so it was great getting the technology out of UTD and a real win. At the acquisition from DM, the university, did very well. There continue to be ongoing royalties back at the university, which is exciting for the university, but it's at terms and a rate such that Desktop Metal and Adaptive can do very well commercially, and it doesn't constrain our ability to go and build great innovative products.
Right. And that's always the problem. It's either they get, somebody at the table gets overly greedy and suppresses the other side, whether it's the commercial terms or the university, and particularly with a state university. Right.
And so much of the leadership at UT Dallas and even at UT System has been embedded with industry. They understand practically what industry needs to survive and to thrive, and have set very reasonable licensing terms to enable founders and founder inventors to commercialize technology. The leadership at UT Dallas has said, we have a state mandate to grow local GDP, to train innovators, to build an ecosystem that can create value. And the early stage stuff at the university is a small piece of that. But if we're too restrictive, it constrains our ability down the road.
Right.
And that's why I think Adaptive did so well coming out. That's why we were an appealing target for Desktop Metal as an acquisition, because we had great technology that had been funded with a lot of non-dilutive equity from DARPA, from federal grants. It wasn't all investor money. There was some investor money, but we were able to de-risk that technology very nicely and provide real value to DM from day one.
Well, and that you were talking about investor capital, because one of the components you need to have to really encourage innovators to step out is risk capital. So where did the original risk capital? I mean, I got the DARPA funding and all that, but that's non-dilutive. Where did you find your risk capital from?
Well, it came from the McDermott family, from the founding family of Texas Instruments. So they had supported my undergraduate fellowship, this Eugene McDermott Scholars Program. Margaret McDermott, who has passed away, gave $32 million to UT Dallas to recruit about 20 students a year to come to the university from across the country and across the world, and said, we want to bring great folks to Dallas and teach you about the innovative ecosystem in Dallas. And I'll take a little aside here. Mm-hmm. I don't know if you know some of the history of Dallas, but it's really quite fascinating. Why we're here. There are no real natural resources, if you think about it. Most of the lakes in Texas are man-made. But Dallas was where three biomes come together. The Great Desert going out past Fort Worth to the west, the Great Plains going up into Kansas, kind of the foothills of the Ozarks. And you had three different horses that rode across these different biomes. And so it was a Native American trading ground for horses. Well, because of that, when railroads got big, Dallas missed out. You had Chicago, Topeka, Baltimore, Santa Fe, St. Louis, big railroad hubs, not Dallas. Because of that, when airlines got big, Dallas said, hey, we missed the railroad bubble. Let's invest in aviation. That's why DFW's here, Love Field, a great cargo airport. And because of that, that's where all the money for oil and gas exploration came. It was on the East Coast, the West Coast. Production was in Houston. So folks drove up from Houston. People flew into Dallas from both coasts, and the deals were made in Dallas. That's why Texas Instruments spun out. They were looking for oil, and the money was in Dallas. So because of that, the integrated circuit was developed here. There's this history of electronics, all because of horses and this punctuated evolution. And that's led to now manufacturing, the next generation of polymer additive manufacturing being here in Dallas.
Yeah, it is. People, again, I was talking about this in an earlier interview with Mayor Volker about these things are generational.
Yep.
They're not the quick and turn. We always think about quarterly results with Wall Street or whatever, but it's the long-term committed bet, committed effort that sees these kinds of results.
Absolutely. And we have this long-standing innovative ecosystem, and it was really some of the early pioneers from TI that helped establish that here, that led to the telecom corridor, that have led to great companies that are in the Richardson IQ, like Zyvex, that have been here since the mid-1990s, that have built this innovative ecosystem based on electronics processing that's now driving this next revolution in additive manufacturing.
Yeah, let's talk a little bit about the Richardson IQ because, you know, there's a lot of parts and groups within the United States who've all tried to kind of name an area, you know, whether it's Silicon Prairie in Illinois or wherever, right? But there, you know, every time I've gotten involved and I've looked, you know, been on the phone with mayor, or now that I'm here this week, this is different. This isn't just lip service of draw a circle around an area and naming it to try to have it some kind of magically poof appear. This has been an effort over an extended period of time and cooperation, public and private.
Well, it has been, and we have the confluence of a lot of the right factors that make this happen. We have that background intellectual capacity from UT Dallas, from Texas Instruments, from Raytheon, from AT&T, from a lot of the great companies in the area. And as you know from being in industry for a long time, you know, some folks stay in a company their whole careers. A lot of folks hop companies and exchange ideas and best practices. And so there's this burgeoning innovative ecosystem of startups coming out of UT Dallas, coming out of SMU, Southern Methodist University. There are a lot of the seasoned mentors and advisors that have been in the telecom corridor that are at TI that want to engage with young folks, with students, and help them pursue the next generation of ideas, whether it's quantum computing or artificial intelligence or additive manufacturing or a host of other buzzwords, you might say, CRISPR technologies, gene editing technologies that are coming out of UT Southwestern. There's just this innovative ecosystem around of people wanting to solve problems. And I think the attitude here in Texas is when there's a problem, you don't necessarily look to the government to have it solved. You roll up your sleeves and go solve it. And I think Mayor Volker and Richardson has embraced that attitude from his time at HP and has put that into civic life and said, hey, let's let government do what we can do. Let's build an infrastructure and set up a culture that can recruit companies, that can give favorable tax treatment, but let this ecosystem flourish. And that's why we're so interested in being here and staying here. And we're excited to be part of it.
So I've been involved both at HP and even in my current role of partnering with universities, funding professors and grad students and postdocs, research efforts. If a listener is interested in partnering with a university, you've had experience, and you know, like everybody, we all have good experiences or bad experiences. Is there any advice you would give to companies when they think about how to best partner with a researcher like yourself or students and those types of things? Because I think for a lot of people, it's just not on their radar screen.
Absolutely. Funding work at universities, partnering with universities, engaging in senior design projects at universities is a fantastic way to leverage expertise that's maybe outside of a company's core. So in a lot of cases, industry will get very narrow. I'm a computer scientist by training, undergrad in CS and a master's in AI. And so there are these two search algorithms. One is called depth first search and one is called breadth first search. And a lot of times in companies, you start off exploring the world, you come up with a temporary monopoly, you really exploit that monopoly, you get very deep very quickly, and then make a lot of money doing so. But a lot of times that puts on the blinders, and you're at risk from orthogonal technologies that can, you know, obviate what you've been doing and come up with new, better ways to do it. Engaging with the university helps take off those blinders. It lets companies at a very early stage see a lot of these other vectors that are heading deep. They might not be deep yet, but that are pointing deep, and gives companies an ability to adapt to them or at least plan for them. Mm-hmm. And I think that's a key aspect that a lot of companies may miss. It's not that the university is going to invent your next great project or product all on its own, but what it may do is give you the intellectual perspective of where science is headed or where technology is headed to help you, you know, be on the right track and not get caught flat-footed. And now some rare times there's great technology that comes out of the university and gets translated. And we were very fortunate to be in that case and be able to rely on great technology from the university. But success of funding academic research isn't just, I've got translatable IP. It's, hey, I've got an understanding of how the world ought to be. where the world is headed, and I can adjust my priorities as a corporate sponsor accordingly. That's why we, even as a small company at Adaptive, continue to fund research. We've supported UT Dallas. We've supported researchers at Caltech. Julia Greer is one of the great researchers in the world in micro and meso-architected materials. Her lab studies this balance between bulk properties and surface properties as you microarchitect and nanoarchitect materials. And we learned a lot of perspective from her and her group, even though exactly what we did didn't become a product. That way of thinking and solving problems has been innate in our strategy for helping drive additive manufacturing forward. So it was an overwhelming success, even though in this case, Caltech didn't see a licensing revenue.
Well, and you bring up an excellent point, right? It's not always about transfer and commercialization. For me, when I look over my history of funding university research, one of the biggest direct benefits, one is thinking, but a more direct benefit is recruiting.
Absolutely.
Getting the best students and seeing the ones you're like, okay, I like that thinking process. It's different. They're looking at the problem differently. They bringing a completely different skill set to the organization.
Absolutely. And at the university, I think at great research universities like UT Dallas, like MIT, like Caltech, faculty are teaching students how to think and not what to think. And by engaging in sponsored research, just like you said, you get this interaction with students that have different perspective, that solve problems in new and clever ways. And it's not even about solving problems. Sometimes it's about finding problems. It's about framing the debate, framing the story, understanding what a real problem is. And this hierarchical thinking that comes out of computer science that's dominant in materials is so important. Often in material science, you want to solve a problem at the macro scale. Well, it involves solving that problem at the meso scale or the micro scale and then translating it back up to a large part. That's exactly what we've been able to do in additive manufacturing.
So as we wrap up, I have one question I always like to ask guests, right? So given your scope, doesn't have to be even tied to additive manufacturing, but what one innovation are you hoping to see in your lifetime?
Wow, deep question. I think it would be artificial general intelligence. A lot of the work that we're doing in material science, in processing light and patterning information is at a level of complexity that we can't fathom in our brains. It's too many numbers. If we take these DLP chips of patterning 9 million bits 10,000 times a second, and now we do this over many, many DLP chips, we're talking about trillions of bits of information every single second. It takes incredible compute power to understand what to do. And I think as we harness the way that people think, but at a speed that computers think, and if it's done in the right ways, regulated in the right ways, and I do think the U.S. is doing a very good job of that so far. DARPA's doing a great job of that, and others. We will have this transformational ability to process goods and to enable services that improve the quality of life, tremendously. And I think if it's done again in the right way, society will benefit immensely.
Well, that's a perfect way to end the show. Well, thank you for joining us on Killer Innovations.
Phil, thanks so much. It's been great to be here.
Thank you. Since the time I've left HP, I've always been tracking the market segment around 3D printing. It was something that was being worked on while I was there, and now HP and many others are active in the market of additive manufacturing. Very unique kinds of approaches. This will be transformative, and I hope this interview that you just listened to with Walt Voit gives you some insight into what's coming, but more importantly, not a futuristic view, but what you could do today with these forms of technologies. If you're building something that's hardware related, parts, products, those types of things, take a look at these technologies. There's firms and approaches you can get online. You can send them your designs. They'll manufacture these parts, send them back to you very effectively from a standpoint of cost and volume. check that out, help you speed up your process, but also 3D printing, pretty cool. With that, thanks for joining us today. Your time is valuable. We value the time in your schedule you take to listen to this show. And we strive to earn that commitment that you have by producing great content. If you've got feedback on today's show or any show, please send it over. Phil@killerinnovations.com. Would love to hear any feedback you might have, such that we can improve the show and deliver content and information that helps you change the world with your ideas and with your innovations. The other question I have for you is, what topics would you like to hear? Things that we're not covering. We do these interviews, but we also do shows around specific topics, something, whether it be leadership, career development, personal creativity, commercialization, execution, launching of product, whatever it is, let us know. We would love to hear that so that we can make sure we're delivering that content that you are interested in. Also, help us pay it forward. The whole purpose of the show and the content being available the way it is because of a challenge from my mentor to pay it forward. And the best way for me to pay it forward is to find those people who can benefit from this information. So help me pay it forward by letting other people know. Give us a review over at Apple or Spotify or iHeart or wherever it is you listen to this show. We greatly appreciate it. And with that, thanks. We will be back soon with another episode. Talk to you later. Bye-bye.
Podcasting nonstop since 2005, this has been the Killer Innovation Show on the Innovators Network.
This show is distributed by the Innovators Network. For more information and other great shows and content, visit theinnovators.network.